Alright everyone, I'm here to tell you about the unsolvability of Quintic equations. And we get to have a special guest. Are you ready to meet the special guest? I think you're ready to meet the special guest. Oh my goodness, is that Mr. Incredible? That is Mr. Incredible. He's here to tell us about how to solve, or the unsolvability of Quintic equations. Wow, thank you Mr. Incredible. Are you ready? Uh-huh. Oh, he told me yes, he's a bit shy, so he probably won't be speaking. So I'll do the speaking for him. All right, we have this equation, ax plus b equals 0. I'm pretty sure you could probably figure out how to solve for x in this situation. Doesn't require a lot of thinking power. Pretty simple, pretty straightforward. Now, this is what we like. This is the quadratic formula. As math majors and professors, this should be second nature for us. We should be able to bang this out like the ABCs. We even have a song for it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is like a mathematician's wet dream. This is so simple, we love it. One of our favorite formulas ever. Hopefully. Now, this is for the quadratic formula, so we have an x squared. I wonder, what would it look like for the x cubed? Because believe it or not, it does exist, and it also exists for a quartic. So that's x to the fourth, plus x to the third, plus so on and so forth. So let's look at the one for the cubic first. Yeah, so that's that. It's a bit difficult. You probably can't memorize it, but I mean, you could probably do it by hand. It's not that bad. It could be worse. It could be worse. It could be worse. All right, now if this is the one for the cubic, let's look at the one for the quartic. Oh boy. So you can't really see it all. Here, you know what? I actually take the liberty of zooming it in for you so we can view it in its full glory. All right, so this is where it starts. Okay, so it's a bit complicated, but you can probably manage. And then it goes on, and then it goes on, and then it goes on, and on, and on, and I'm pretty sure that's it. So that's a lot. That's a lot of numbers, and imagine doing that by hand. I would not be happy. That would be me. I would be Mr. Incredible. That would be my face. I would not be a happy person solving that equation by hand. So, now I'm sure you're wondering, if that is what it looks like for the quartic, what in the world is that equation for the quintic, and do I even want to lay my eyes upon it, or do I just want to run away as fast as I can? Well, I'm here to tell you that it's impossible. It was possible. The formula never existed. And I know, mind blown, so crazy. Like Mr. Incredible, that's all over our faces right now. Now I'm here to show why. Thank you, Mr. Incredible, for that great thumbs up. All right, let's look at the four most important notable people for this proof. So this is a bit before, well, this is like 4 people before, and then we'll have a bit of a time skip, and then we'll look at more people after this. So here are our 4 most important people right now. Scipione del Ferro, Niccolo Tartaglia, Girolamo Cardano, and Lodovico Ferrari. I did not look up how to pronounce their names before recording this, but it's too late for that now. Alright, so we have a bit of a timeline for us. So, Del Ferro, in 1515, Del Ferro creates a general solution for the cubic equation, but he never publishes it. In 1535, Tartaglia also found a solution for the cubic equations, but it had nothing to do with Del Ferro, so he did it completely independently of Del Ferro. It was his own thing. Then, in 1539, Cardano convinces Tartaglia to share the solution he found. And then in 1539, they accomplished this by Cardano and Ferrari working together to create a more general solution. And once they have that, Ferrari can now create the general solution for the quartic equations using info from the solution to the cubic equation. And finally, in 1545, Cardano publishes the Ars Magna, which means great art, which contains the solutions for both the cubic and quartic equations, while citing all of these 3 people, Tartaglia, Del Ferro, and Ferrari. All right. What about the Quintic equation? Because we just looked at the cubic equation and then we looked at the quartic equation. You may be wondering, this is about the Quintic equation. What's next? Well, to do that, we have to look at three more people we have the three more important people to look at. We have Paolo Ruffini. I don't think that's what he looks like. Oh yeah, I'm pretty sure that guy from before was an actor who has the same name, so not sure how he got there, but anyways, we have Paolo Ruffini, Niels Henrik Abel, and Évariste Galois. I had to look up how to pronounce his name. So, we also have a timeline for this as well. In 1799, Ruffini writes an incomplete proof that is difficult to follow and contains a logical fallacies. I believe even like Abel, when he went back and looked at Ruffini's like incomplete proof, even he said that it was like complicated and difficult to comprehend. So I don't even want to know what it looks like to the like a average Joe Schmo like me who can barely write a proof on his own. So in 1824, Abel writes the first valid proof of the general Quintic equations. We'll look at that a bit more later. Abel refines and expands on his proof from 2 years before in 1826. So he rewrites it, he makes it better, I suppose. I'm not sure how that works, but he rewrites it. In 1830, Galois creates a type of group theory that reinforces the proofs of Quintic equations. Now, and as you can see, in 1832, he unfortunately dies, and in 1846, his work was published, meaning if you put two and two together, you can figure out Galois actually never published this group theory that he figured out because he passed away. And I actually have a live reenactment of how he passed. So I believe it was due to a duel. I don't believe it was Mr. Incredible that he was dueling, but he did die. So unfortunately, he passed away. His work was not published, at least for a few years after that. It looks like, what is that, 14 years? I'm a math major. I should be able to figure what 46 minus 32 is. So about like 15 years or so later, his work was finally published. And this the Galois theory, the principles and concepts from there is what a lot of the more modern age proofs use to prove this Abel and Ruffini theorem that Abel proved in 1824 and 1826. All right, let's get to the proof. Now, I could have you read my entire project proof, but just to save on time and to make it a bit simplified, I'm going to give you the simplified version, you know, the Sparks notes of it. All right. For a polynomial equation to be solvable by radicals, this is a term you'll come up and to see quite a bit often as you see polynomial equations being solved by like certain formulas. It has to be solvable by radicals, which means it must be able to find a root using only addition, subtraction, multiplication, division, and nth roots. So pretty simple, like just basically multiplication, like the most basic operations in math, and nth roots. And then Galois theory, that's the thing that Galois taught us when that was his work. It tells us that a polynomial is solvable by radicals if and only if its Galois group is a solvable group. Now, those are two things that you might not know, Galois groups and solvable groups. So, a Galois group is a group of all the possible permutations of the roots. So, okay, that's not too bad. So, and then we have the solvable group, which is a group of finite subgroups that can be broken down until all the subgroups are abelian. So it's basically a group, and every single subgroup, and it's not an infinite amount of them, all the subgroups within it are broken down to the point where each one of them is abelian, and meaning that they can commute. Now, let's call the possible permutations of all five of our roots S5, which is the symmetric group of 5 elements, aka all the possible ways of writing 5 different elements. So like, for example, we include the first one, the third one, the fourth one, or we include the second one and the fifth one, or we include just the fourth one, or we don't include any at all. So there's a lot of different permutations that we can go with. Now, contained within, that's backwards. That should not say S5 within A5. It should say, oh wait, no, that is right, never mind. Contained within S5 is A5, which is known as our alternating group, which is defined as the group of even permutations of 5 elements. So, again, another definite thing you might not know was an even permutation. So, luckily, I have that defined for you. An even permutation is a permutation that, when broken down into only transpositions, and remember, transpositions are two-cycle groups, so basically they just swap with each other, has an even number of those transpositions. So, going back, remember that we have 5 elements, and every single permutation of 5 elements can be broken down into only transpositions, but we are only looking at the even permutations, which contain an even number of those two-cycle transpositions. All right. Now, here's a special note that we must know. A5 is only a certain number or a certain amount of permutations of 5 elements, and S5 is all of the possible permutations of those 5 elements. So we can confidently say that A5 is a subgroup of S5. This isn't important immediately. It'll probably come up just a bit later, probably like I'm not sure how long I'll take this, like a minute or two, but I'll get to that when I get to it. All right, another thing to know about A5 is that it's, quote, simple, meaning it cannot be broken down into any possible smaller subgroups. So all of its small groups are as small as they can go. Now, something else we can also find is that A5 is not abelian. We can look at this by composing 1, 2, 3, and 3, 4, 5. And I'm taking I'm not sure if it's what the standard is, but I'm going from right to left. So, as you can see, if you compose 1, 2, 3, 3, 4, 5, you want to take a second to do it, you get 1, 2, 3, 4, 5. But when you compose it oppositely, so when you swap them, 3, 4, 5, 1, 2, 3, you get 1, 2, 4, 5, 3. So that means that A5 is not abelian. So like I said before, this is a very simplified version, so there may be some gaps in logic, and I'm kind of jumping to conclusions here just for the sake of time and simplicity, but just take my word for it. All right, from before, remember, this is the thing I mentioned before, Galois theory tells us that we must have a solvable group. Remember, we must have a Galois theory tells us that a polynomial is solvable by radicals if and only if its Galois group is a solvable group. So we must have some sort of solvable group. But our solvable group is not abelian, and remember, a solvable group must have a finite number of small subgroups that are broken down until they are abelian. Well, A5 is broken down as much as it can be, and it is not abelian, meaning A5 cannot be is a solvable group. And since A5 is contained within S5, remember we proved that it was a subgroup of S5, that means that S5 is also not a solvable group, meaning it cannot be solvable by radicals. So, therefore, there is no general formula to represent all the roots of a polynomial equation of 5th degree or higher. Now, I'm not sure how exactly that works, but because we only proved it for the 5th degree, but I'm sure it relates to the higher degrees, like 6th degree or 7th degree. Whew, that was a lot. I understand if that would be pretty difficult to wrap your head around, because it was for me the first time I did it. All right, what did we learn? Well, we figured out that, how do we solve this? How do we solve this Quintic equation? Well, honestly, I don't know. Just use a calculator, because there's no general formula for it, as we literally just proved. So, not the quadratic formula. It's not as easy as that. So, you're on your own. I'm sorry, you're on your own. All right. Thank you for watching. Thank you, Mr. Incredible. You carried the team. Thank you, honestly. Thank you, Mr. Incredible. And thank you for watching. And then here is my references, page 1 and page 2. Thank you very much for watching. Bye-bye.